Hello world, in today's video we're going to be looking at drawing free body diagrams as well as force diagrams. Okay, so these properties which I wrote across, they are applicable for both the force diagram and the free body diagram. The ones which I just wrote on the left, they are only applicable to the force diagram. So when we draw free body diagrams and force diagrams, we draw these diagrams to try and show the forces that can act on an object. So in drawing the force diagram, the object is represented with a block. So if you have a whole car there and we want to show the forces acting on a car for a force diagram, we're just going to, instead of drawing the car, we're just going to draw a block. That block will then represent the car. The forces are drawn using arrows because remember that forces are vector quantities, and to represent the vectors we use arrows. And then it says all arrows must be appropriately labeled. So if the arrow represents the normal force, then you must clearly label it as discussed in the previous video. And then the length of the arrow is proportional to the magnitude of the force. If I draw this force and I say this is, for example, kinetic frictional force, and then I draw this as the applied force, from the length of the arrow I can tell that this arrow is shorter, meaning the magnitude of the force will be small. This one, because it's longer, it's going to have a larger magnitude as compared to what? As compared to the kinetic frictional force. Then the other one says arrows must touch the block. So if this is the applied force and I'm drawing it, it is very important that the force apply must touch the box. If you draw the force applied some distance away from the applied force, then that will be marked incorrect. And then it says that arrows must be drawn where the forces are exerted. Let us say, for example, we want to draw the kinetic frictional force. Let us say that car is moving towards the right. Remember, the kinetic frictional force is opposite to the direction of motion. And what we have said is the kinetic frictional force is a force that opposes motion. What is causing it? It is causing by the surface that the object is in contact with. So that force is applied there on the tires because the tires are the ones which are in contact with the surface. So that force is acting somewhere there at the bottom of the object. So if I were to indicate it, I would draw it somewhere there. So this will be the kinetic frictional force. If you want to draw the normal force, remember the normal force is a force that is being applied by the surface. But what is in contact with the surface? It is the tires. So it means that the normal force is acting on the tires. So you're going to draw it starting there at the bottom, at the tires. And the tires would be somewhere there at the bottom. So for every object, the normal force always starts from the bottom of the box. So that will be the normal. Remember, when you draw the normal, we draw it perpendicular to the surface. But when we get to the free body diagram, instead of using the block, the object is just represented with a dot. And all arrows, they must touch the dot. So if this is your kinetic frictional force, it must touch the dot. So all the forces that we're going to be drawing on the free body diagram, they all start on the dot. So if it's kinetic frictional force, it starts at the dot. If it's normal force, it's also going to start at the dot. Remember, all the objects that we're dealing with here, they have mass, and they're all going to experience the gravitational force. They're going to have weight. So drawing the weight as well, we are going to draw the weight pointing downwards. Remember, the weight is always vertically downwards. That will be the weight, and it also needs to start from the dot. Normally when we draw these magnitude of the force, when we draw the the length of these arrows, we don't normally take into account the relative magnitude. So the statement over here, we hardly apply it unless stated so by the examiner. So I realized that with the force diagram I never showed the weight. So the weight is a force that acts from the center of the object. So the weight, we always draw it from the center of the object on a force diagram. So let us just go ahead and take a few examples. So an object of mass m moves to the right across a smooth surface. Smooth. What is that telling us? Smooth is telling us that there is no frictional force. So if I were to draw a force diagram, I need to take this object represented with a block. Because it is in contact with the surface, I am going to have normal force perpendicular to the surface. I am going to have weight from the center of the object, so this will be weight. And as we see from the diagram, we are having a force applied. There's the force applied. We draw the force exactly where it acts. So that will be the applied force, F, and we don't have any frictional force because they said that the surface was smooth. So to summarize this, when you draw the normal force, you just draw it starting from the bottom of the block. The weight, you draw it from the center, and then all the other forces, you can draw them from the surface of the block. And then when we get to the frictional force, just to make this a norm, you can always draw a set of axes before you draw the free body diagram. How do you choose your set of axes? Remember what we said in the previous video. The x-axes are parallel to the surface. Those will be x-axes. Y-axes will be perpendicular to the surface. And where they meet, that's where you put your dot. And you can start drawing the forces. Remember the forces, they all start from the dot. You have the normal force pointing upwards. You have the weight always vertically down. And finally, we have the force applied, F. So that will be our free body diagram. So, but let us try to change that statement a little bit. Let us say that the object of mass m, I wanted to say mass m, moves across, I'm going to remove the smooth there, moves across a rough surface. Remember when they say rough surface, it is telling us that there is friction, and you need to decide on which one it is. Because it is moving, it means we are dealing with kinetic friction. So I'm just going to draw only the free body diagram for this one. So you're going to have your y-axis perpendicular to the surface, x-axis parallel to the surface. Where they meet, you can draw the dot. The weight, which is a force that the earth exerts on an object which is on or near its surface, represented by W, is always vertically down. You have normal force. Remember that normal force always points away from the surface, perpendicular to the surface, away from the surface along the y-axis. That is my normal force. And force applied, we can see it's along the horizontal direction. That is our force applied. And this time around, I said rough surface, so it means that we have kinetic frictional force. If the block is moving towards the right, then kinetic friction will be opposite the direction of movement. Remember we said frictional force always acts parallel to the surface, meaning that it's always along the x-axis, which are parallel to the surface. So that will be kinetic frictional force opposite the direction of motion, and that will be my free body diagram. So let us take another example. Please feel free to pause and try this out for yourself. Okay, this is the same thing. This one says a small object of mass 2 kilogram is sliding down at constant velocity of 1.5 meters per second down a rough plane. Rough. This tells us that there is friction. What kind of friction do we have? We first need to check if it's moving. Yes, it's sliding down, it's moving. So we have kinetic frictional force. And we are being told that it's moving down a rough plane which is inclined at 7 degrees to the horizontal surface. So there's our surface there. Remember, along the surface or parallel to the surface, that's where you have your x-axis. Perpendicular to the surface, you have your y-axis. So I have something like this. X-axis, y-axis, y x. Now I can start drawing my forces. Where the x's meet, I can put the object. Remember, when we draw the weight, we said the weight is vertically down. Normal force away from the surface, perpendicular to the surface. So that will be my normal force there. Normal force. Which other force do I have? We also have kinetic frictional force. Because this object is moving down the slope, kinetic friction will be opposite to the direction of motion. Remember, it must be parallel to the surface. So this will be kinetic frictional force. Okay, so let us look at another example. So for this example, I'm going to draw the free body diagram for both the blocks. Let us rather start with the first diagram. So the statement says a 5 kilogram block resting on a rough horizontal surface. Rough tells us that there's friction there. We just need to figure out which one. And is connected by a light inextensible string passing. Oh, wait, they are talking about a string. Remember, if there's a string, then it means we have tensional force. So they say that the string passing over a light frictionless pulley to another block of mass 2 kilogram. The 2 kilogram block hangs vertically as shown in the diagram below. A force of 60 Newton is applied to the 5 kilogram block at an angle of 10 degrees to the horizontal, causing the blocks to accelerate to the left. So both the 5 kilogram, my apologies, is accelerating towards the left. But before we start, let us check, do both of these blocks have normal force? With the 5 kilogram block, yes, it does, because it is on a surface. With a 2 kilogram block, the 2 kilogram block is not in contact with a surface, so it does not have a normal force. So let us start with the force diagram for the 2 kilogram block. So the force diagram, I'm going to represent this with a block, and this is going to have weight from the center, so this will be the weight. And because there's a string there, then it means I'm going to have tension. How do we draw the tensional force? Remember, we draw it along the string away from the object. So what this tells me is that the tensional force will be along the string away from the object. That will be my tensional force. When it comes to the 5 kilogram block, I have the weight, I have the normal from the bottom of the block, I have tension. How do I draw tension? Along the string away from the object. So that will be the tensional force. Remember the assumption we make about the tension? We assume that the tension is the same throughout the string, cable, or rope. And then we also have the 60 Newton force. Where is the 60 Newton force acting? It's acting somewhere there. So it's either you can write 60 Newton or you can label it force applied. Because we spoke about rough horizontal, it also means that we have frictional force. And because we were being told that this is accelerating, it's moving. So it means that we have kinetic frictional force. It will be opposite the direction of motion, so it will be towards the right. So this will be kinetic friction. So if I need to draw the free body diagram, I just simply need to replace the block with a dot. There's the tensional force. So this is my free body diagram, FBD. I'll be using that for free body diagram. And then that will be the weight. And when I get to the 5 kilogram block, in blue are my free body diagrams, by the way. In blue, I will have my weight acting vertically down. Let me just include my axis. I am also going to have tension. Let me make this big enough so that all the forces can fit. I'm going to be having tension. I'm also going to be having kinetic frictional force. I also have normal force, perpendicular, and away, pointing away from the surface. And lastly, I have the force applied, which is somewhere there at an angle. So I'm going to say force applied. That will be the free body diagram. I think that's it for me for today. Till we meet again, thank you all.